This lesson is on current. And current is one of the most important concepts in the study of electricity. Now, previously we've talked about this idea of charge, and that charge can build up in static electricity between two insulators, and that there are two types of charge, positive and negative. Now, in a conductor, charges can flow freely, or when you have a build-up of static electricity and you get a spark and a discharge to a conductor, you're getting a flow of charge, a flow of electrons from one position to another. So if you think about a metal, and we think about metallic bonding, which is something that you should know both in chemistry and in physics. Metallic bonding consists of a lattice of positive metal cations. And just to clarify, cations are positive ions, so metals always form positive ions. So we will have a lattice, which is this structure, this shape of positive metal ions, and then surrounding each of these we will have some electrons, and because these atoms in the metal, their shells overlap with each other, some of these electrons are free to move around. So we call these electrons delocalized or free electrons. And what that means is that they are free to flow, and if I just choose one as an example, through the metal. Now you can see that the path that I've just drawn wasn't a perfect straight line, and that's because electrons, if you think about it, don't have a sense of direction. They don't know where they're going. But if I apply a potential difference, if I apply a voltage across a section of wire, what I'm going to do is I'm going to encourage the electrons to travel or drift in one direction. Now, electrons themselves travel incredibly fast, hundreds of meters per second. But in terms of how fast they travel down the wire, they travel very, very slowly. If you have a circuit like this, where you have a power supply, in this case this is a battery, and a bulb, the electrons here at this point will only move incredibly slowly and drift around at a rate maybe of half a centimetre a second. They're very, very slow. But the electrons themselves are moving very quickly. So the reason for this difference is that the electrons are colliding with the positive metal ions. So we have what we call electron-ion collisions. And understanding electron-ion collisions is key to understanding some of the issues surrounding electricity. So the more electron-ion collisions we have, the greater the impedance, which means the greater the effect of slowing down the electrons is. So certain materials have a greater tendency to do this for whatever reason. Maybe they have more positive metal ions in a smaller space, so they're denser. Maybe the wire is thinner, and so the electrons and ions are all bunched together. They don't have much space to move around. But anything that affects electron-ion collisions is ultimately going to affect the resistance. And this is an idea that we will come back to at a later point, because resistance is an important concept in electricity. But what we're going to focus on this is current. So we've already talked about this idea that electrons will flow through the metal lattice and will collide with the ions, but overall they will drift along the metal wire. And this is what we mean by current. So the definition of current is the rate of flow of charge. Now, it doesn't say the rate of flow of electrons, and the reason is because you can have a current which isn't electrons. So in electrolysis in chemistry, we have the movement of ions, which are charged particles. but they aren't electrons. So we have to be a bit more broad than just saying it's the flow of electrons. Also, the idea of rate is important, because whenever we use the word rate in science, the word rate means divided by time. So as an equation, and the symbol for current is a capital I. The reason it's capital I is because originally it stood for electrical intensity, and C is used for something different. That's used for capacitance. So in the symbol for current is capital I. So current is the rate, which means divided by time, of the flow of charge, how much charge we have. The symbol for charge is Q, because like I said, C is already taken. C is taken for capacitance. So Q is the symbol for charge. We have time, and we have current. So if we were to rearrange this equation, which you should be able to do, we can also write it this way. Q is equal to I times T. And we have time is equal to Q divided by I. I quite often remember the equation in this form, and I call it the quit equation, because it looks similar to the word quit. So it's the way that I remember it, but how you remember it's up to you. The other thing you need to know is the units of each thing. So we measure current in amperes. 1 ampere is 1 coulomb, which is the unit of charge. So coulomb. So that's the unit that we have for charge. So 1 ampere is 1 coulomb per second. So obviously the unit of time is always seconds. So charge will flow along a metal wire, and the rate at which it does this, how fast effectively it travels along this wire, we call current. But it's not just about how fast, it's also about how much. So you can think of current very much like how much traffic there is driving down a road. Okay, and that's a useful analogy to have. So if I've got a lot of cars, or a lot of electrons, then I'm going to have a much bigger current. And if they're travelling very, very quickly, then obviously I will have more cars pass me in a certain amount of time. So again, I'm going to have more electrons pass me, so I'm going to get a bigger current. So think of current very much as the number of electrons that are passing a point every single second. Now, if we relate this to an electric circuit, so we've got a battery here, and we have just an arbitrary output. In this case, we've got a bulb. We think about the way that current flows around here. Now, before we discovered the electron, and obviously you should know that an electron was discovered in 1897 by J.J. Thomson. Before we discovered that, the device that Thomson used required electricity. So we had to understand electricity before, in terms of how it works and how to use it in circuits and build devices, before we were able to discover the particle we now call an electron, and we associate with electricity. So scientists had a decision to make. Now on a battery, the longer end is the negative, and the shorter bit is, the longer end is the positive, my apologies, and the shorter end is the negative. So I always remember it as thinking that I could take the longer end, snap it in half, and make a little cross. So that's the positive, and the shorter end is the negative. So they decided hundreds of years ago that by convention, current was going to go from positive to negative. So we call that conventional current. And so we always say that current goes from positive to negative. That's conventional current. Now, if you think about that for a second, you'll realise that, well, electrons are negative. So electrons are going to be, so if I've got an electron here that's negative, it's going to be attracted to the positive, so it will flow in the opposite direction. So electron flow is negative to positive. So we have these two conflicting ideas, but it's important you understand both. So conventional current is positive to negative, And this is the one that we use when we're analysing circuits. So we still use this convention that we pretend current goes from positive to negative. Whereas in reality, the flow of electrons is negative to positive because the negative is attracted to the positive side. So we have conventional current, positive to negative, and electron flow, negative to positive. One final thing to think about with current is the current at different points on the circuit. So I could measure the current at this position before the bulb and after the bulb by putting in an ammeter. So an ammeter is what we use to measure current. And what I would find is, let's just say for example that the current here was 5 amperes. The current over here after the bulb would be 5 amperes. And it hasn't been used up. And the way to think about this is, imagine at this point here is a speed camera, okay, on the road, and I had 5 cars passing the speed camera. I would still have 5 cars at the end of it. The speed camera doesn't destroy the cars, it doesn't use up the cars. All it does is the cars pass through it. So with current, the current in a series circuit like this, which is one loop, is the same at every single point on the circuit. And so in order for a current to flow, this demonstrates we have to have 2 key things. One, we have to have a complete circuit. Current won't flow if there's a break in the circuit. So if I was to melt the wire here, current would not be able to flow all the way around, and therefore I wouldn't get an electric current. And the second thing that I have to have, as well as a complete circuit, is I have to have a potential, an electromotive force, which is another phrase for voltage, effectively. I have to have a power supply, in this case the battery. The battery provides the electromotive force, or the EMF, and that is the push to make the current flow around the circuit. So I have to have a complete circuit, and I also have to have an electromotive force that's going to ensure that my current flows around my circuit. So to summarise, current is the rate of flow of charge. It is how much charge is flowing through a current at any one point. It is the electrons themselves travel very quickly, but the rate at which the electrons travel through the wire is very slow because of electron-ion collisions. However, I will just point out that if I switch my battery on, there is no delay whatsoever between when I switch the battery on and when the bulb will light. And the reason for that is because if the electrons at this point move, all of the electrons move. So if, for example, if I was to move this electron here along the wire, it would create a space which this electron would simultaneously move into, and this electron would simultaneously move into. So all the electrons move in one go around the circuit. So there's no delay between the battery being switched on and the bulb. And lastly, we have this idea of conventional current, which is positive to negative, but we understand that electron flow is negative to positive. You should also be able to use this equation in calculations.